So molarity is molality. Molarity is a unit of concentration, and molarity is calculated by taking the moles of solute and dividing it by the liters of solution, shown with the capital M. Molality, shown with the lowercase m, is found by dividing the particle moles of solute divided by the kilograms of solvent. So there is a difference there. First of all, notice we have kilograms of solvent versus solution. So it would be, say, the amount of water versus the whole solution. And the particle moles, that is another key difference. Let's discuss what that means, this idea of particle moles. So some substances, for instance, NaCl, table salt, when it dissolves in water, it dissociates into sodium ions and chloride ions. So this is a strong electrolyte. Something that dissociates into ions. So in 1 mole of sodium, 1 mole of sodium makes a total of 2 particle moles, right? 1 of sodium and 1 of chlorine. So it breaks up in water into 2 moles of particles. Now that makes a difference when we think about things that are affected, properties of solutions that are affected by the number of dissolved particles, like the colligative properties, the boiling point elevation expression, which we'll look at tomorrow. Now take this other example, C6H12O6, which is the formula of glucose. Now glucose is a non-electrolyte, so when it dissolves in water, these are in water, it does not dissociate. It still continues to be C6H12O6. No dissociation occurs. So in this case, with a weak electrolyte, 1 mole of glucose is also 1 mole of particles. So 1 mole glucose is also 1 particle mole. So this is going to factor in when we calculate molality. What is the molality of particles in a solution of 125 grams of magnesium chloride, a strong electrolyte, dissolved in 0.5 kilograms of water? So we have the amount of the solute, so the mass of the solute is 125 grams MgCl2. Then we also have the mass of the solvent. The mass of the solvent is 0.500 kilograms of water. Now the molality equation is, lowercase m is the particle moles of solute divided by the kilograms of solvent, which would be water in this case. So the key here is we need to figure out what the number of particle moles are. And in order to do that, we need to look at this compound, MgCl2. MgCl2, when that is added to water, it dissociates into its ions. We did this back in section 12.2. So remember doing dissociation, where we look at how things break up into their ions. That's what we're doing here. So it breaks up into Mg, 2+ ions, and chloride ions. There are 2 chlorides, however. So in total, 1 mole of the compound MgCl2 broke up to make a total of 1 here plus 2 more there, or 3 particle moles. So 1 mole equals 3 particle moles. 1 moles of MgCl2 equals 3 particle moles. So with this link, we can now figure out the number of particle moles in 125 grams of magnesium chloride. So we set it up. We can start with our 125 grams MgCl2. We'll need the molar mass to convert that to moles. So for every, the molar mass is 95.3 grams MgCl2 per mole, MgCl2. And now we use this link right here. For every 1 mole of MgCl2, we have 3 particle moles. So this will give us the number of particle moles. Calculate that, and it comes out to 3.93 particle moles. Now the last step is we plug that into the molality equation. Molality, again, is particle moles of the solute divided by the kilograms of the solvent. So the particle moles we just found, and it's this number right there, so we just plug that in. And the kilograms of solvent was given to us in the problem as 0.5 kilograms. So we plug those numbers in, and so we have 3.93 moles. We can just put moles, and that's divided then by the kilograms of the solvent, 0.500 kilograms. Calculate that, and the molality comes out to 7.87 molar. And I had carried out the digit, so that's why it rounded up. I think if you plug in 3.93, it's 7.86. All right, so let's do another example. Calculate the molality of a solution containing 35.5 grams of glucose in 0.4 kilograms of water. So in this case, we have, just use some scratch paper here. So this time we have the mass of the solute as 35.5 grams. And so that's of glucose, C6H12O6, and the mass of the solvent is 0.400 kilograms, and that's of water. And so we want the molality. Now, just like the last problem, we need to think about this compound, glucose, C6H12O6. Now, C6H12O6, when it dissolves in water, what does it do? Is this an ionic compound, one that dissociates into its ions like the last problem? Well, no, it's a molecular compound and a non-electrolyte. So it's a non-electrolyte. And as a non-electrolyte, it doesn't dissociate. It continues to be a molecule of C6H12O6 when it dissolves. So in this case, the number of particle moles is equal to the number of moles of the compound. So moles, so for every 1 mole of C6H12 H12O6, we also have 1 particle mole. Well, that makes our life a little easier. We can just start then with the grams, convert it to moles, and plug it straight into the equation. So we have 35.5 grams of C6H12O6, and we'll need the molar mass. Convert that to moles. The molar mass is 180, so for every 180 grams of glucose, we have 1 mole of glucose. And so that results in 0.197 moles of glucose. So now we can plug that into the molality equation. Molality is the particle moles of solutes divided by the kilograms of solvent. Plug those numbers in. Here's the moles of the solute, since it's the same, particle moles are the same as the moles of glucose, and the kilograms of solvent given to us right here is 0.4. So we have 0.197 moles of glucose divided by 0.400 kilograms. And so the molality in this case is 0.493, or let's see, we have to be 0.493 molal. So read the lowercase m as molal.